So we've done our exponential graphs. Now let's look at our logarithmic graphs. I guess in general, the parent function would be log base b of x equals y for any log graph. So in this case, we have a log base 2 of x is equal to y. We're going to go ahead and graph that. Some special logs we need to know about. Just like a square root is really an implied index of 2. If you see a log x, that's an implied log base 10. We call that the common logarithm. If you see a natural log, that's how this is stated. Natural log of x, that's the same as the log base e of x. All right, so that's just for future reference. Log base 2 of x, we need to set up a chart, plug in x's and y's. Now remember, this says what power of 2 is this number? So I need to pick powers of 2, like a quarter, a half, 1, 2, and 4. So what power of 2 is 4? That's 2. What power of 2 is 2? 1. What power of 2 is 1? 0. What power of 2 is a half? Negative 1. And what power of 2 is negative 2? And you'll notice this is the exact flip of an exponential of 2 to the x, and that's because these are inverses. So we take a look at the graph of this. I have, let's go over a quarter and negative 2, somewhere around here, a half, negative 1, 0, 1, 2, 1, and 4, 2, like such. So this graph is going to look like this, which kind of is similar to a square root graph, but it goes forever in both directions. Now you'll notice that we can never have a negative log, because what power of a positive 2 would give you a negative number? That's never going to happen. So this will never go to the negative side. So the domain's always greater than 0. So this actually has basically a vertical asymptote, if you will. Moving forward, we see that we have an a value here and an h value of negative 1. Everything else is 0. So I know that k is 0 and b is actually 1. So what I'm going to do is I'm going to back up 1, put my crosshairs, and then again look at that pattern for x and y of log base 2 of x, a fourth, a half, 0, 1, 2, and 4, 2, 1, 0, negative 1, negative 2. And then I'm going to multiply all those by 3. Negative 6, negative 3, 0, 3, 6. Start from here. I have 1, 0 again. Now I have over 2 and up 3. Over 4 and up 6. Half down 3, quarter down 6, doesn't flatten out quite as much, still have our asymptote, but this time it's at negative 1. Now we're going to add a k, and we're going to make our a value a negative, so that should flip the graph over the x-axis. We have a equaling negative 4, b is 1, h is 2, k is 3, go over 2 and up 3. That's going to be my new origin. I'm going to go log base 3 this time, so I need powers of 3. 9, 3, 1, 1/3, 1/9. 2, 1, 0, -1, -2. And we multiply all these by a -4, getting -8, -4, 0, 4, and 8. So if I go over a 9th, I go up 8. If I go over a 1/3, I go up 4. 1, 0. Over 3, I go down 4. And go over 9. And down 4 more. So here's my graph. And I've actually committed the cardinal sin in my previous examples. I walked away from the problem without checking. How dare I do that? Let's take a point, 5, -1. Plug it in here, make sure it works. So I got -1 equals -4 log base 3 of 5 minus 2 plus 3. This is -4. Log base 3 of 3 is 1 plus 3. -4 plus 3 is -1. Check. So now we've got a situation where b is going to enter the problem, but this isn't in the right form because I need a coefficient of 1. And this is also log base 10. Just for fun, I know I'm going to rewrite this by factoring out a 4th, saying I have x here plus 8 plus 3. So a is 1, b is 4, because that'll put that 4 in the denominator down here. H is -8, and k is 3. Let's go ahead over to -8 and go up 3 crosshairs. X, Y. I'm going to go 10, 1, and 1/10, because otherwise it's going to get too hairy. This is a 1, 0, and -1. And we're going to multiply the x values. Holy cow, this is not going to be pretty. By 40 or by 4. Holy smokes, this is ugly. 4, 4, or 44 and 4/10. Holy cow. All right, so this is my x. Didn't think that out very well. Anyways, let's take and go to 4, 0, 1, 2, 3, 4. Right here, over 4/10, down 1, over 40, which is way the heck over here, up 1. This is going to be a super flat guy. It's going to take forever to get over here, like so. Let's just use, oh, what the heck, -4 and what is that, 3? Check that point. Pretty sure it's going to work. So I have y, or 3 equals log base 10 of -1 or +1/4 times -4 plus 2 plus 3. So this goes to 1/4 times -4 is -1 plus 2 is 1. What power of 10 is 1? That's 0. 0 plus 3. Done. Check. So something like that. And keep going here. We're going to solve for some log problems now. This is very similar to our introduction to our exponential equations. Again, not trying to insult intelligence, but if I know that the log base 3 of x plus 5 is equal to log base 3 of 3x plus 2, it stands to reason then that x plus 5 has to equal 3x plus 2. So I have 2x is equal to 3, and 3 halves is equal to x. Now again, you can only do this when there's one logarithm on each side that's isolated and they have the same base. Likewise here, one log on each side, same base of 10 in this case. Set x squared plus 8 equal to 2x squared minus 6x minus 4. So I get x squared minus 6x minus 12 is equal to 0. So I think I'm going to go ahead and complete the square, which means I'll isolate the variable terms. Take half and square, so add 9 and 9. Have x minus 3 quantity squared, 21. Square root both sides, so I have plus and minus root 21 equals x minus 3. So 3 plus or minus root 21 is equal to x. Now, the root of 21 is not quite 5, it's about 4.5-ish, let's say. All right, so what I need to make sure is that when I take 7 and plug it in here, I'm not going to have any negative numbers. And this is not going to be a problem. However, when I take a 3 minus 4.5-ish, I get negative 1.5. That's not a problem. And this probably won't be a problem either because this is a positive number. If this is a negative 1.5, this is positive. And then this is positive. I'd say this is probably okay. And that's all we've got for today. We'll talk to you next time.